This is the uniform disk problem. So we have a charge Q distributed uniformly over the surface of a disk with radius r. So I'm going to assume that the disk is thin. That means its thickness is negligible. And then we consider a point on the symmetry axis of the disk. So let's remember that the symmetry axis is that line that passes from the center of the disk and it's perpendicular to the plane of the disk. Right? This is basically the symmetry axis. So we consider a point on that line with a distance z from the disk, and we would like to compute the electric field at that point. This is one of the problems that we can solve, but by doing a proper integral, obviously. So we are going to discuss about this. So let's just say a few more things in here. I said that z is the distance, but we can take it as the z coordinate. So this is the z-axis basically, and we choose this point as the origin. And with this, basically this point has a z coordinate, which is equal to the given by z. Right? Let's just keep this in mind. What else? So I think that's it. So then I pass on discussing the problem. So how do we solve this problem? Basically what we need to do is to divide this disk into small rings. And we have just deduced the electric field produced by a ring. And so therefore by using this, we can compute we can form some kind of an integral, and from the integral we can compute the electric field. So first things first, we need to define something called the surface charge density. Right? This is usually shown by the Greek letter sigma. So that's basically defined as the charge divided by the area. So in this special case, we have a charge Q distributed over an area of pi r squared. And so therefore the surface charge density is given by that quantity in here. Let's just say that the distribution is uniform if and only if the surface charge density is constant. So any non-uniform surface distribution would have a surface charge density sigma depending on the position on the surface. Here it is independent. So basically I can take any piece of surface in here, compute its area, multiplying the area with the density, I can find the charge in there. Right? Let's just keep this in mind. Okay, so let's then think about this approach in here. So as I have said, what I need to do is to divide this or think of this disk as a union of small rings. I'm going to show it like that, but this is just one of the drawings in here. So I'm going to think of it like that, and then concentrate on one of these rings, compute the electric field produced by that ring at that point, and then integrate. Okay, so let me go ahead. So this time I'm just going to exaggerate everything. So this is the big disk. This is the center. So this is the point in question. What I do is I just consider a ring in here with inner radius r and outer radius r plus dr, where dr is infinitesimal. So I'll try to draw this as best as I could. But let me show it like that. This is r plus dr. And we are considering only the charges in here on that ring. Right? So again, let me write it in words. So we consider the ring with inner radius r, outer radius r plus dr. and I would like to find the total charge in here. So there's some kind of a charge in here, dq, and I would like to find what that charge is. That's basically sigma multiplied with the area of that ring, and this area is basically given as, area of the ring is given as the circumference, which is 2 pi r, multiplied with the thickness. So I'm assuming that this thickness of the ring dr is infinitesimal. So as a result, I can easily write this thing down. So there's no approximation involved in here. Basically, in the limit where this dr is infinitesimal, this is the correct expression. In any case, this dq is a charge which is distributed over that ring with radius r. And I know that this thing in here, that ring, is going to produce an electric field at that point, which is the electric field at that point is dE. That's basically due to that charge dq in here, which is given as, I'm just going to write down the formula for the electric field produced by a ring in here, ring with radius little r, r squared plus z squared to the power 3 over 2. This is basically the z component of the electric field, but it's also the same as the electric field produced by the whole ring in here. Okay, so this dEz is the electric field produced by that ring only, but we would like to consider the effect of all of the possible rings in here, starting from rings with radius 0 up until to the rings with radius equal to capital R. And so as a result, I need to compute this. It's the integral of this expression, dEz, right? So that's an integral of 1 over 4 pi epsilon 0 dqz divided by r squared plus z squared to the power 3 over 2. And then I need to write down dq in here in terms of my variable. My variable of integration is basically little r. Let me do that. So that's 1 over 4 pi epsilon 0. Sigma is in here, and then we have 2 pi r dr multiplied with z, and then divided by r squared plus z squared to the power 3 over 2. So once I obtain this expression, I just stop and look at this expression in here. So all I need is an expression that involves constants like this one, or sigma. I know that sigma is constant, or 2 pi and z and whatever, and the variable of integration. So here the variable of integration is little r. That's basically the radius of the rings in here. So the little r is the radius of integration. So as a result, the only expressions in here is the variable r and the constants. So this is basically, once I notice this, and then after that I just write down the integration bound. So I know that the disk has an, let me say it like this. The little r variable ranges from 0 to capital R. So therefore 0 and capital R are the integration boundaries. Okay, so that's basically the second to last step. So the very last step is to use your calculus knowledge and then integrate this. So let's continue and do it like this. So I'm sigma and whatever, all of these quantities are constants. So just take these constants out of the integral. So sigma is in here, 2 pi is in here, z is in here, 4 pi epsilon 0 is in here. That's it. And then we have an integral from 0 to capital R of r dr divided by r squared plus z squared to the power 3 over 2. Okay, so the rest is calculus now. And then at the end we are going to summarize the results. Now, let me first of all say it like this. I usually do these kind of expressions like this. This r dr is basically 1/2 of the differential of r squared. This is basically a change of variable, but without formally defining the variable that you are changing it. So as a result, you can think of it like, you can write this expression as, forget about integration bounds. So that's the differential of r squared divided by r squared plus z squared to the power 3/2. So by just looking at that expression, you can see which variable should you define for the change of variable thing. So you're going to call this r squared as the new variable u. Let's continue like that. So once you have the name for the variable u, then you can write down the values of the boundaries, the integration boundaries in terms of u. So let me do it like that. So that's 1/2 of du divided by u plus z squared to the power 3/2. And integration boundaries are from 0 to capital R squared. Yeah, it's taking too many steps in here, but let me write this thing down like that. So that's u plus z squared to the power minus 3/2 du. So it's a power of u essentially. So forget about this. So the power will be minus 3/2 plus 1. So therefore this is minus 1/2. And then I have to multiply it with minus 2 so that if I take the derivative, this expression just goes away. So that's the integral. So if you want, you can basically change it to the radius variable and then write down the integration bounds in terms of the radius variable. In any case, this is the integral. I think I'm going to cancel these two. So I'm going to write down the value of this thing in terms of the capital R. And then, well, this is the one that I compute in here, and then subtracted the value that you would get when you insert 0. Okay, so that's the expression in here. So let's just write this thing down in the way that we would usually write them down. So that's the 1 over the square root of r squared plus z squared. And this is plus 1 over the square root of z squared. Now I write it down like that because on purpose. Basically we have to take the square of z and then take the square root. So people usually tend to write z in here, but unfortunately this is not the case. That's basically the absolute value of z. So let's just keep in mind that z can be negative in these expressions. So to be able to apply the formula for those cases as well, I'm just going to use this convention. So as a result, I'm just going to write down the absolute value of z in here. So let's go back to the expression in here. So that's easy. So let's just remember this. So Ez is equal to sigma times 2 pi times z divided by 4 pi epsilon 0. And then I have an expression which is the 1 over the absolute value of z minus 1 over r squared plus z squared. Okay, so in any case, let's see these two cancel each other. So this is like sigma over 2 epsilon 0. And then we have z divided by z minus z divided by the square root of r squared plus z squared. Right. Well, this is basically the signum of z. So there's some kind of a sign involved in here. So let's say it like this. So sigma over 2 epsilon 0. And then we have, this is 1 minus absolute value of z divided by the square root of r squared plus z squared times signum of z. Right. That's the expression that we can write down. But just keep in mind that sigma is not a given quantity. It's just an expression that we have deduced, that we have used at intermediate stages. So let's just express everything in terms of the given quantities, which is basically the charge and the radius of the disk, and z. So therefore, in terms of this, the electric field is given as Q divided by 2 pi epsilon 0 r squared 1 minus z divided by square root of r squared plus z squared times sigma of c. Okay, so there are a few things that we need to talk about this, but since there are a lot of few things, I'm going to postpone them to a different video. But we have to actually try to interpret this and then try to see what kind of a function is this. Okay, so as a result, I'm going to postpone them, but this is an important part of the discussion. Just keep this in mind.